I'll be showing you everyone how a X-ray generator works. They call it an X-ray generator, even though it's really just a transformer with a very large diode on it. I have it hooked up to a variac, otherwise known as an auto transformer, to control the voltage input. And this here is a microwave oven transformer with the high voltage secondary shorted to the case, and the primary in series with the generator. We do that to limit the current. Doing this is called putting an inductive balun. I'll be controlling it with a variac, otherwise known as an auto transformer. These allow me to adjust the voltage level to the X-ray generator. And this is a microwave oven transformer with the secondary shorted, the high voltage shorted to the case, and it is hooked in series with the generator. We do this to limit current. This setup is called an inductive ballast. And as the current through the wires rise to the generator, the inductance will drop across the ballast, causing more voltage to drop across, again, the microwave oven transformer, the ballast. This will limit the current going to the X-ray generator. And a little thing about X-ray generators is they are used to power the X-ray machines you find in your hospital. They use extremely high voltage in what's called an X-ray tube, which is an old type of vacuum tube that's still used today in X-ray machines. They're very large and they operate in anywhere between 50 and even up to 400 kilovolts, 400,000 volts. They do this so they can generate the X-rays needed to go through your body and take the image of your bones or whatever they're trying to, doctors are trying to look at. And this is just the power supply for one. This particular one is a Philips, made 1987, I believe. It is was used out of an X-ray machine, but is now spare parts, and it does work. This particular one will go up to 80,000 volts, 80 kilovolts at full power. And I'll be powering it again with a variac. And for this test, in the beginning of the video, we're just going to power it with a residual voltage coming out of the variac, which is about 0.6 volts AC. Over here. This is the circuit we're looking at. This is the input from the wall, the 120 volts AC, because we are in the US, 60 hertz of course. AC sine wave coming in. This is the auto transformer, also known as a variac, and has a variable secondary that can go from 0. But in this case, it's not 0, it's 0.6 because there is some residual voltage in the transformer. And it can go all the way to 130 volts. Today, we'll probably only bring it up to 100, but its capabilities do go to 130. I would never bring the X-ray generator above 120 because that is what it's rated for, and I don't want to burn things out. This is the MOT, also active. In this case, it's acting as a ballast. We short the secondary, so there's a maximum current going through the secondary. And again, that is to limit the current going through this circuit here. And this circuit is the X-ray generator. It has a few turns on the primary, just very few, and a whole bunch of turns on the secondary. The ratio of this particular transformer, I'm not sure. It is well over 1 to 200. And this here is the high voltage diode acting as a single rectifier diode. They do this because it's a lot cheaper. A full bridge rectifier would be more efficient and better, but these diodes are incredibly expensive because they are handling 80,000 volts at a pretty decent current. So this the AC sine wave gets rectified by the single diode, and if you were to look on the oscilloscope, you'd see every other little peak there in positive. So it's taking this peak, the negative peak here, and eliminating it through the diode, if you don't know how diodes work, and only the positive peaks are left. In a full bridge rectifier, which just doesn't have, again, it's too expensive, Instead of eliminating this peak, it would reverse it, and you'd have all positive peaks back to back. In this case, we don't. One more thing here before we get started. This is the output, the high voltage, 0 to 80,000 volts output, and that's got some really nice insulation on there, of course. That goes into the ground is just the chassis ground, which is grounded to earth through this here. I'm just using some Romex to power it, the 120. This is the primary coil, which sits between 0 and 120 volts. This here is the grounding. On here we ground we ground the secondary's low end, which comes out here to the chassis ground here. So the 2 points we're going to be measuring from are ground of the chassis, which is basically everywhere, and the output here, which is going to be the positive voltage. So let's power it up. I'm just using standard 120, but for this test, you see I have the variac cranked all the way down to 0, and the residual voltages in the variac make it not perfectly 0. I'm going to reset these meters just to make sure they don't die on me. So we got this meter is measuring voltage AC coming from the variac. You can see it's almost nothing, which is good. Just the residual voltage in the atmosphere is what it's picking up. This one is set to 1,000 volts DC. For this test, we will not be going over 1,000 because I really do not want to damage my meter. And before I hook everything up, I make sure this is off. Make sure we're at 0. Take this, which is going to be feeding our X-ray generator, plug it in here, and we're going to turn it on. When we turn it on, you'll see our meters jump because the residual voltage in the transformer, even though it is set to 0. Here we go. About exactly 0.6 volts AC is coming into the generator, as seen here, and we're getting 32 volts DC out of the X-ray generator, which is pretty decent rise there. Now you might be wondering why, how could it be 80,000 volts when we only have such a small ratio? I mean, 0.6 to 32 volts seems like it would be about 150 to 1, well, 1 to 150 ratio on a transformer. But that's not the case. The reason is, come back here, this diode has a diode drop. Most silicon diodes have a diode drop, a forward diode drop, of about 0.7 volts DC. However, to handle the sheer amount of voltage and current that's going through it, they had to make the diode much, much larger, and we're expecting about 400 to 600 volt drop across the diode. I can't be sure without taking it apart and measuring it, but again, the transformer is filled with oil, and it would be a big chore to do that, and it's really not necessary for what we need. I did look up the specs. It will put out 80,000 at full power. All right, here we go. Stick with us. We're going to go to our next video, which you'll be seeing the transformer at about 100 volts in, and we should be expecting over 50, maybe 60,000 volts out, and you'll get to see those arcs here in a minute. Be right back. All right, guys, now that we're set up for high voltage, we're going to be putting a low spark test first. That's going to be at 20 volts in. Should be a few hundred volts out. Actually, we'll probably be over 1,000 volts out, but that's just to make sure it's working. And we'll do that first, then we're going to ramp it up to half power at 60 volts. That should give us a few dozen kilovolts out. After that, we'll bring it up to our full 120 volts, and that should get us to quite a bit of voltage, maybe even 80,000 volts, and we'll see it jump the arc. This is a chicken stick I have. It's made out of fiberglass, non-conductive, and that is strapped and ground here, grounded with the X-ray generator. And this here is our high voltage output again. So we're just going to get right into it, and we'll see what these high voltages can do as they break down the air. All right, let's bring it up to on, and bring up to 20 volts AC input. Now we're at 20 volts input. We'll expect 1,000 to maybe 3,000 out. And again, we'll just see the arc come across here and see those work. Yep, and that's just our little, relatively low voltage. Relatively, couple thousand volts. I'd say between 1 and 5,000 volts. I don't have a meter that can measure something that high without blowing it up. So that is our low voltage test. Let's bring it up to half power, which is going to be at 60 volts AC input. Alright guys, now we're at 60 volts. So I'm expecting to say 20, 30,000 volts out of here. DC, here we go. My knowledge says that's about, say 200, not 200, 20 kilovolts, plus or minus 5 or 10,000 volts. And then it's half power. Let's bring it up to full power, which is going to be well over 50 kilovolts. Hopefully, maybe we'll see the 80 kilovolts. Let's go ahead and bring it up. And this will be our full power arcing test. Now that we're at the 120 volts, we're at full power, and you can't hear it, but I can. There is some ionization of the air, where electrons are being stripped out of the air to our high voltage here. And we're going to watch what 80,000 volts, or to be honest, I'm not exactly sure how much, but we're going to see some pretty decent voltage arcs here. Going to readjust. Alright, well, let's ease the voltage back down to be nice to our transformer. Hey guys, to make it seem this much better, we turn the lights off in here, and we're going to do some arcs at full power with darkness. So here we go, some even brighter arcs. That's darkness. You can see a lot brighter arcs coming out of this thing. Alright, now we should be back at 0 volts. Just for safety purposes, I'm going to unplug the transformer there, and there's going to be some residual voltage there caused by the capacitance of the inductor. The transformer is going to hold some voltage in an electric field, and what we're going to do now is discharge that before we do any more adjustments. Here we go. So that would have hurt very, very badly if I thought, oh, there's no more power to it, but in fact, that residual voltage stayed there. So now that it's at 0, it's unplugged. My next step would be to measure up the meter, make sure it's at 0 volts. But that is, but I'll do that after the video, but That is our test today of a Philips X-ray generator transformer, or what is commonly called an X-ray generator, at few dozen volts DC. I'm estimating by what I saw between 50 and 80 kilovolts. I'm not sure exactly what it's rated for. I can't find the data, but it is very high. This power supply is going to be used in my new project build that I have designed and will start putting together soon, called a nuclear fuser made by Dr. Farnsworth, and no, not the one from Futurama. The original Dr. Farnsworth, who also invented the first television. Therefore, I'm going to use this to power that. And I'll get to the science of that in the next video when I finish the nuclear fuser, and I'll update anybody who is interested on my progress as it is developed. Most nuclear fusers use what's called a microwave oven transformer, like our one there. However, that one only puts out about 1200 volts. And we want to ramp that up to something pretty serious, and we'll see what happens, and if we are able to fuse any hydrogen into helium, preferably deuterium. But again, that's a topic for another video. That's how an X-ray transformer or X-ray generator works, and that is my demonstration for the day. Thank you for watching Lakeshore High Voltage, and hope to see you again soon.